Okay, now let's talk about the other property of a continuous functions. 3.28 lemma. Start from a lemma. The sign preserving property. Okay, so let f from I to R, where I is an open, non-degenerate interval. Okay, if f is continuous at a point x0 in I, and fx0 is greater than 0, then there are positive numbers epsilon and delta, such that ops value x minus x0 less than delta implies fx greater than epsilon. So here epsilon and delta are both positive. Okay, so this lemma looks very technical, quantitative, but the geometric idea is very, very clear. So remember, we're talking about a continuous function. Continuous function means the graph is going to be connected. Well, it's like a line. We don't have connectedness so far. So a graph is like you can sketch it without lifting your pencil. That's normally what people can describe. So it's like this. Whatever, it can go continue up or it go down. It doesn't matter. And for some point x0, fx is positive. Maybe this value is very tiny, but you just amplify your rescale your system so that it looks like very big. Okay. So assume at point x0, the value is like this place. Then definitely you see, because you have this continuous graph close to it, you can always find a narrow region, small enough region, so that over this interval has length 2 delta. You move to the left delta, move to the right delta. Okay? Over this interval, so that this whole piece of a graph is above epsilon. Is above epsilon. It's always above epsilon uniformly. Right? So that's basically the idea of epsilon and the delta. So when fx is close enough, it's not for all epsilon. If you choose epsilon to be a million, of course, not every fx will be greater than a million, right? So there are epsilon and delta. This epsilon normally will be very, very tiny. This delta will be also very tiny, but it's positive. Okay? So there are, not always, not for all, there are. Okay, so let's see how do we prove it. The idea is it's just this geometric graph, the proof. So this is fx. What is epsilon? So naturally we can say, okay, let's just select half of fx0, half of xx0, f of x0. You can choose whatever rational part of fx0. Okay, it doesn't matter. So, but normally here you can say, given epsilon equal to fx0, based on our selection, possibly we have 2/3 of fx0, right? It looks, I mean, my selection is like almost the 2/3 of fx0. Anyway, it's just a positive number. It's positive, a reasonably positive number. Okay, then for this epsilon, then you can choose delta greater than 0 such that whenever you have x minus x0 less than delta, it implies fx minus fx0 ops value is less than epsilon, right? Less than epsilon. Well, let's see what this is. This is a fx minus fx0 less than epsilon greater than negative epsilon. So it's a negative 2/3 fx0 less than fx less than 2/3 fx0. Oh, epsilon is here. And then you add fx0 for all three sides, you will get 1/3 fx0 less than fx less than plus it's 5/3 fx0. But it doesn't matter. We do not need this part. We only need this part. Okay. So the epsilon actually now you can see that if we choose 1/2, here is still 1/2. But if you choose 2/3, this becomes 1/3. Okay. Then 1/3 of fx0 and delta will work. Well, this step epsilon is not this epsilon. It's this epsilon is from the definition of continuity. We should. It's better for us to just put prime. Epsilon prime is not the epsilon we're talking about. So this one is epsilon. You redefine this 1/3 fx0 to be epsilon. Okay, so that's a proof. The proof is very trivial. It's a direct property of a continuity. So this is a property of a continuity, another property. In the last video, we have the property of a continuity, which is a upper bound, lower bound, extreme value theorem. You can reach the supremum and the infimum over the closed bounded interval. Okay, closed bounded interval. But here, this interval is just open, non-degenerate interval. It's not necessarily closed and bounded. Okay? This is a local property. That one is also local, but it's over into. Here is a very, very local. Okay, so here I rescale it to be epsilon prime. This is epsilon prime. Okay. The name is not that important. Okay, so this is a sign preserving property. If you have a point positive for a continuous function, then in its neighborhood, certain neighborhood, it's always positive, uniformly positive. Clearly, if this function is negative, if f is continuous at x0 and fx0 is negative, then definitely there are positive numbers epsilon and delta such that x minus x0 less than delta implies fx is uniformly less than negative epsilon. Be careful, here I use negative epsilon to guarantee it's a negative number. Epsilon delta, they're both positive, but I put a negative sign to guarantee it's negative. You just flip it. You just flip it down to the below the x-axis. You will have it. Right? Okay. So based on this property, we're going to study the other very, very important property of a continuous function. It's a intermediate value theorem, the IVT. For the continuous function, one is the extreme value theorem, EVT. The other one is the intermediate value theorem, IVT. They're both important. Okay, in the IVT part, statement of IVT, there's a statement here. A point, a real number, y0 is said to lie between C and D. If you have a number, it's between the other two numbers, C and D, if and only if either. So here, I don't know what is the relation between C and D. So we have two possibilities. One is C is less than D, the other one is D is less than C. So either, oops, sorry, it's not delta, it's D. Either C is less than Y0 less than D, or D is less than Y0 less than C. Which is those two cases correspond to the two possible relative relations between C and D. Okay, either this case or that case. Okay, that's just a terminology, what we mean lie between other two numbers. Okay. Now let's see 3.29 theorem, intermediate value theorem. Intermediate value theorem, intermediate value theorem. Okay, so let I be a non-degenerate. Non-degenerate means you really have an interval. You do not just have a point or some empty set. Non-degenerate interval. And f from I to R be continuous. Okay. If A be in I with A less than B. So you have an interval, it could be closed or open. Here we don't require it's an open or closeness. And you pick up 2 points and you specifically require A is less than B. So you can construct a small interval. This is I. Here's A, here's B. Because I don't know the closeness or not, so I just draw it. I don't mention it, but you have A and B with this relation. And if Y0 lies between FA and FB. Okay. So possibly, let's put it here. This is FA. This is FB. So Y is at this level. Y0. Then there is an x0 in the open interval AB such that fx0 is equal to y0. What does it mean? You see, you have a continuous function, then you just have a graph. Connect FA and FB. And then you have this y0, the horizontal line. Well, based on the graph, you can see that we must have an intersection. We must have an intersection. And this intersection is on the graph, so it has x coordinate, x0. Fx0 is equal to y0. That's what this theorem says, IVT says. We all know what this meaning, right? From the calculus, we have this. But in the calculus, we just demonstrate by this. We say, okay, because of this, so IVT works. Now, in this class, we're going to literally prove why this is correct. Okay? So, because of this definition, lie between 2 points, you have two possibilities, but those two possibilities are symmetric. Either C less than D or D less than C. There's no difference between those two possibilities. So here, we can say that without loss of generality, we assume that FA is less than FB. FA is less than FB. Then, if this happens, well, then I think we should actually just directly write this way. Y0 is between FA and FB means FA less than Y0 less than FB. Okay. Well, this point is lower than Y0. Just consider the set E. Set E is the point X in the closed interval AB are both in I, so this is closed interval. With the property Fx strictly less than Y0. Okay, so possibly it's like this interval. This is E. Without this X there. So first we get A in E is not empty. And second, E belongs to AB. Is not empty, E belongs to AB, so it's a bounded non-empty set. So E is a bounded non-empty set in R. Bounded non-empty set in R, then by the completeness axiom, the x0, which we define it to be the supremum of E, is a finite number. Whenever you have a bounded non-empty set in R, then it always have a finite supremum. Okay. So here, x0, we're going to say x0 is not equal to A and x0 is not equal to B. Why? The reason is the following. Why x0 is not equal to A and x0 is not equal to B? Fa is less than y0. Then remember that there are positive numbers. Epsilon and delta, such that for x minus A less than delta implies Fx is less than y0 minus epsilon. See, here I actually use the sign preserving property in the general way. how general? Some preserving property says fa is less than 0, then fx in the neighborhood is less than negative epsilon. 0, here I replace it by y sub 0, y sub 0. If it is less than y sub 0, then of course it's going, in a small neighborhood, it's going to be less than y sub 0 minus epsilon. Right? So by this property, we can see that the point x equal to a plus, let's just say, delta half still belong to E. From here you can get this one because f a plus delta over 2 is less than y0 minus epsilon. I don't know if it plus delta is less or not, but delta plus over 2 is definitely satisfied. So it means this so this implies x0 is going to be strictly greater than a plus delta over 2, greater than or equal to. X0 is greater than or equal to a plus delta over 2, right? It's a supernorm. Supernorm is greater than or equal to whatever point inside it. So x0 is not equal to a. And similarly, with the same reason, similar, not the same, similar. Because if we are talking about b, then here is fb is greater than y. Fb is greater than y, then it will be y0 plus epsilon. Okay, with a similar reason, x0 is not equal to b. If you want, I can write it down. Fb is greater than y0, then there are positive numbers epsilon and delta, epsilon and delta, such that x minus a less than delta implies fx is greater than y0 plus epsilon. It's always above y0. So x equal to, not a, this is b. It's b. b minus delta over 2 belongs to e, because fb minus delta over 2 is no, I think no, sorry. Yeah, it's a good question. Why? Ah, okay. Now I see I make some mistake. E only works for right. So no. I think I made a mistake. Yeah, it's not right. It's not right. E only works for fx less than y0. It does not work for fx greater than y0. So we can get x0 is not equal to a, but why x0 is not equal to b? Why x0 is not equal to b? Well, it's a set. If x0 is equal to b, then f x0 is equal to fb is strictly greater than y0. Strictly greater than y0. And if this happens, then what we have for then for x0 is a supermem. Wow, it's so interesting. X0 is a supermem of E. Okay, so let's see this. Fx0 is greater than y0, then there are positive numbers epsilon and delta, such that x minus x0 less than delta implies fx is going to be greater than y0 plus epsilon. Y0 plus epsilon. Yes, it's greater than epsilon. Greater than y0. You just consider this y0 as a 0. It's a sign preserving property. Yeah. Okay, so it implies. So what this means? This means x equal to x0. This part minus delta over 2. Minus delta over 2 is fx0 minus it's greater than y0 plus epsilon. Okay, so you just choose you have a x0, move to the right, left delta to the right delta. So I choose this part as x as x0 minus delta over 2. I want a smaller number. So this implies x0 minus delta over 2 does not belong to E. So actually it is a supermem. The upper bound, it is an upper bound. But less than x0, which is a supermem of E. It is an upper bound, but less than supermem. It's a contradiction. Hence, the contradiction comes from your assumption. Okay, the contradiction comes your assumption. The supermem is the smallest upper bound. This x is less than x0. Strictly less than x0. So here we want to say it's upper bound. So let me make this clear. We want to say this x0 is also upper bound. It's because this x0 now is a b. This intersect of y is empty. So from every point from this interval, it has a ups value greater than, has a value greater than y0 plus epsilon. So it does not satisfy the condition of E. So the E looks like this is E, this is X, X0, which is B. So the whole thing are not inside E, so this part does not contain any element from E. So this X is an upper bound, it's greater than whatever value from psi. Okay? So that's make it a contradiction complete. So we have to claim it's an upper bound, otherwise it's not that obvious why it is an upper bound. So okay, so let me make myself clear this time. Again, I think I didn't explain it very clear. So first, we construct a set E bounded and non-empty. Then we have a supremum. And this supremum, we want to claim this supremum is not equal to A and not equal to B. But these two situations come from two different reasons. Not equal to A, we start from the sum preserving property. Fa is less than y0, then there's a small neighborhood so that fx is always less than y0 minus epsilon. Okay, y0 minus epsilon. You just consider y0 as 0, less than 0, less than 0 minus epsilon, negative epsilon. Okay, so it means in a small neighborhood it's going to be less than y0 minus epsilon. Okay, y0 minus epsilon. So this interval, this whole interval, a plus delta over 2, a plus delta over 2, it's always inside E. The whole thing is always inside E, then x0 is going to be greater than a plus delta over 2. Okay, so x is not equal to a, x0 is not equal to a. So this is the reason. It's depend on the definition of E. Now let's talk about why x0 is not equal to B. Assume x0 is equal to B, then we use the same property, the sum preserving property. Fx0 is equal to Fb is greater than y0. Greater than y0 means you have a small neighborhood. You have a small neighborhood so that inside this neighborhood, Fx0 is going to be y0 plus epsilon. Y0 plus epsilon. Over the whole interval, this whole interval, Fx is going to be greater than y0 plus epsilon. And it means this whole interval intersect E empty. So there's no element from this left part of the interval. Then we pick up x as x0 minus delta half. Then we pick up a point x here. Then this x is an upper bound of E, but it's less than the supremum of x0. Less than supremum of x0. It's a contradiction. Supremum is smallest upper bound. So it implies this x0 is not equal to B. Okay, so this time is correct. My previous idea was not correct. I didn't recall that the definition of E. Okay, so from those two parts, we get a conclusion x0 belongs to open interval A and B. X0 is not A, X0 is not B. So the reason we cannot directly say X0 is not A and B is because we get X0 based on the supremum. We don't know the value of Fx0. We have no idea. We're going to show that Fx0 is equal to y0. Fx0 is equal to y0. Okay. So first, choose a sequence xn in E with the limit xn equal to x0. Then we know that fxn is less than y0. Hence, fx0, which is the limit fxn. It's continuity. Here we use a continuity. Continuity means you can pass it to the limit. Interchange with the limit and f. It is going to be less than or equal to y0. Okay, so this place we use a continuity. Literally it is like this, and then it is equal to limit. You exchange f and the limit operation. Okay, now we have less than or equal to. If fx0 is less than y0, then again by the sign preserving, then there are positive numbers epsilon and delta, such that x minus x0 less than delta implies fx less than y0 minus epsilon. If it's still strictly less than y0, then you can always find a small neighborhood so that over the whole neighborhood fx is less than y0 minus epsilon. But this will imply that fx0 plus delta over 2 is still less than y0 minus epsilon. It's less than y0. Okay? You just use a small number on the right side of x0. And this implies x0 plus delta over 2 belongs to E. Less than y0 belongs to E, but x is less than x0 plus delta over 2 contradicts to x0 is a supremum. Supremum is upper bound. It should be greater than. Contradicts to the fact x0 is a supremum. It should be greater than whatever point from inside of the set. Hence, fx0 has to be equal to y0. Okay, fx0 has to be equal to y0. Actually, we don't need to prove fx0. We don't need to prove x0 is not equal to b. We can go through this process. You go through this process, you get y0, fx0 equal to y0, because fa, fb are both not equal to y0, so x0 is not equal to a, x0 is not equal to b. So this part is not that important. Okay, so you can see, check here. This whole thing does not depend on where this x0 is. You can just go through this process. You prove that fx0 is equal to y0, then because of this condition, you get x0 is not equal to a, x0 is not equal to b. Automatically, x0 is in an open neighborhood. X0 is in an open neighborhood. Okay? So it's, well, even though we spend a long time to prove it, but it's not that serious at the beginning. Okay, so in the short way, how do we describe the IVT, intermediate value theorem? It just say the this is finished the proof. Just say that if f is continuous on the closed interval AB and y0 is between fa and fb, well, still we assume fa is less than fb, then there is an x0 in the closed interval AB with fx0 is equal to y0. Here we put an equal sign, so it is in the closed interval a, b. It could be just happen at an endpoint. In the intermediate value theorem, we have strict inequality, so it's in the open interval. Okay. We have continuity. What is continuous? Then what is discontinuous? If it's not continuous, then it's discontinuous. So if f is not continuous at a in I, then we say that f is discontinuous at a. Discontinuous, just not continuous. Okay. The easiest way, the example, not way, the easiest example for the discontinuous point is this. Prove that fx equal to upper value of x over x if x is not equal to 0, because we have x in the denominator. When x is equal to 0, actually you can define it to be whatever number. So in the book they just use 1. And then prove this function is continuous on the negative infinity to 0 and 0 to positive infinity. So here the closed interval means it's continuous from right hand side, but discontinuous at 0. Discontinuous at 0. Both f0 plus and f0 minus exist. Okay, you just use the definition to prove that. And you see that f0 plus, f0 minus, they're different. This is a positive one, this is a negative one, so you have discontinuous point. Okay, remember that. So you just remember that f is continuous at a if and only if fa plus is equal to fa minus is equal to fa. Okay, fa plus, the right limit is equal to the left limit is equal to the value, then it's continuous. And of course, the book tried to give us more examples. fx is sine of 1 over x, sine of 1 over x, and we can say fx is continuous on negative infinity to 0, 0 positive infinity, discontinuous at 0, but f0 plus, f0 minus do not exist. f0 plus, f0 minus do not exist. How do you say they do not exist? You just find one sequence they converge to that limit, the other sequence they converge to different limit. So for example, let's say we choose n pi plus pi over 2. This is sine, yeah. Then the sine xn is equal to 2n pi. Is equal to 1. And yn 2n pi minus pi over 2 sine yn is equal to negative 1, always. But this xn converges to 0, yn also converges to 0. For two sequences, they have the different limit, then the function has no limit at this point. So that's the right part. right part. You can put the negative sign, you get the negative part, Okay, so that's the discontinuous. One more. Well, let me discuss the other two examples in the next short video. The other two examples are related, but is more interesting. Okay, I finished this video, and I will continue discussion in the next video. Thank you.